Okay, so I got booted out of the room I'd found that I think was maybe an improvement. Hopefully this will work out. I'm trying to, I wasn't real happy with there's some glare on the screen last time. Hopefully I've fixed that. So this, you should, if you haven't seen the proton NMR, if you haven't seen the proton NMR theory video yet, you should watch that. Because I'm not gonna really talk about how NMR is taken or what it means. I'm just gonna go through how we analyze one. Okay, so again, just to kind of pick up where we left off on that last video, proton NMR is going to give you 3 different pieces of data, types of data, and you have to use all of them. Again, that's just a science thing, right? You can't just toss out data because you're like, I don't like that. It doesn't fit. You have to use all the data. So you have to look at the chemical shift of a peak in the proton NMR, and that's going to tell you the electronic and magnetic environment that the proton is in, and that's really the frequency domain of the spectrum. You have to look at integration. That's how intense the signal is. All right, the peak area in proton NMR is proportional to the number of protons making the signal, right? So integration is going to tell you how many protons you have making that one signal. And then the most complex piece of data is splitting of that signal, all right? So in C13 NMR, everything's just a line. In IR, you can have strong band, you can have broad band, but it's still just a band. Here, we're going to get detailed information about how many protons are close to the proton causing the signal, all right? And just a word, before we do unknown 2, I'm going to revisit splitting because it gets a little more complex even than what you're going to see here, but I want to start you off as simply as I can. Okay, so here's the proton NMR that I left off with. All right, so in green we've got the chemical shift, and again, consult this PowerPoint when you're trying to work with proton NMRs. Like ideally, like I have this memorized. How did I memorize this? Well, many years ago, I had a professor, Chris Adams, who made me memorize it. All right, I don't like to do that. I think it's really hard to just memorize data that doesn't mean something to you, right? So like you remember stuff that's important to you. So as you go through here and you're working problems, this stuff should stick in your head because it will be important to you. You've got a problem to solve. If you just like try to make a printout of data and go lay in your bed like late on a Thursday night and try to memorize it, like who cares about that data, right? So you're going to memorize stuff that is useful to you. All right, but anyway, chemical shift, like the type of proton, and by that I mean like here's a methyl, you know, there are 3 protons on this carbon. The methyl protons bonded to an aromatic ring. So where will they normally fall? What you'll discover is a methyl group bonded to a benzene ring will fall pretty much in the same place and look the same way in every proton NMR. Okay, so you know, just like if you go back to the very beginning of the intro to spectroscopy, right? Black coffee looks like black coffee, and you can tell how strong it is, right? Strong black coffee, it's black, you can't see through it. So you know it's strong black coffee. If it's, you know, brownish white, somebody's put cream in it. You know that. So just the same, you start to recognize, you know, what a methyl group bonded to an aromatic ring looks like. Okay, but before we do this one, so I asked you at the end of the last video to assign every peak. I guess something I need to say here. So in a proton NMR spectrum, all right, so in a proton NMR spectrum, just like in C13, right? So in C13, every line corresponds to a carbon. In a proton NMR spectrum, every peak is going to correspond to a hydrogen, right? We're not going to see this oxygen. The oxygen's not going to have a peak. We can infer the oxygen from what the peak looks like. So every proton in this molecule has to have a peak in the NMR spectrum. Every peak has to correspond to a proton. So what I wanted you to do at the end of the last video is tell me which peak corresponded to which protons. And again, If you haven't done that yet, you should do it before you see the answer at the end of this video. All right, let's do another simpler molecule first. Oh, look at that. I like to do this when I lecture. Okay, so we've got a spectrum, and you see there's, jeez. This wall is not flush. I almost said a bad word. All right, so nothing down here, right? If we go to the chemical shift, you got protons bonded to sp2 carbons, you got protons on carboxylic acids, aldehydes, none of that. So really, we just have protons on sp3 carbons here. Every one of these signals corresponds to a proton in the molecule. Every proton in the molecule is going to have a signal. So can you figure it out from there? Probably not, right? At this point, probably you haven't done a lot of proton NMR, and so you probably don't have the information or experience to deduce the molecule to fit this spectrum. So let me give you the molecule. If you want to hit pause and give it a try, feel free, but my guess is you're not going to be able to do it. No, wait. Okay, so the other thing is I did all that with chemical shift alone, right? The chemical shift is the frequency axis, no protons on sp2 carbons, protons only on sp3 carbons, chemical shifts. This is probably going to be an H on an sp3C bonded to an electronegative atom. And then 2 to 3 is an H bonded to an sp3 carbon that's bonded to an sp2 carbon, and then down here is just sp3 CHs. All right, that's the chemical shift information. So again, if you want to hit pause and try to work it out, that's cool. The other thing you get, and like I said, you really couldn't have done it with the last data, you get integration. So this peak, 2 protons, this peak, 3 protons, 2 protons, 3 protons. And remember, it's the total area under the curve, and so as the splitting gets wider, the peak gets shorter, right? There's more splitting in this CH2 than there is in this CH2. This CH3 is a singlet, so it's a really tall, narrow peak. This 3 proton signal has got 3 peaks. It's a good bit shorter. Remember, you're looking at area, not height. All right, and then there's the splitting. I talked about this last time. I'm going to write the integrations down here so you have them. Okay, so now you've got all your data. We've got splitting in here. A peak could be a singlet. A singlet's just one line. That means there's no neighbors. There's a singlet here. A doublet. A doublet is going to be 2 peaks. It's going to have 1 neighbor. Again, for the reason why, see the last video. So there's no doublets here. Triplet. This is a triplet, okay? 1 to 2 to 1. That's a triplet. You get 1 to 2 to 1 from Pascal's triangle. Again, see the last video. Quartet. Nope, no quartets. Yeah, no quartets. So a quartet would be 1 to 3 to 3 to 1. Quintet, 5 peaks, nope. Sextet, which I've abbreviated SX, right? You got one of those. 1, 2, 3, 4, 5, 6 peaks. So you see that up here. In Spectra, I give you, if it's not clear, so in real life, you have to figure this out on your own. But in Spectra, I give you for assignments, if it's not clear, I'll write up here what the coupling is. So T triplet, S singlet, SX sextet, T triplet. All right, now with all this information, now if you wanted to hit pause, maybe you can piece together the spectrum. Like I said, I could do that from here. If you don't feel up to it just yet, that's fine. Let's go to the next thing. I'll show you what the molecule is. So if you're going to give it a shot, hit pause. All right, yeah, this is the other thing. This is really important. This is just something I've observed over the years teaching spectroscopy to new students. Like maybe integration makes sense to you and you're like, I'm just going to use integration. Or maybe chemical shift makes sense to you and you're just going to use that. You can't do that. You have to use all three of these. All right, so you have to use the splitting of the peak, and that's just what the peak looks like. And often I'm asked, like, how do you know this is a triplet and not three singlets? Well, it could be three singlets, right? That would be bad luck. Triplets are going to be 1 to 2 to 1. Singlets are just going to be a line. Quartets will be 1 to 3 to 3 to 1. You sort of learn to read that. But yeah, it's a worry, but you should, if you see an integration, if I give an integration, like if this was three singlets, I would say 1 1 1 or 1 2 1 or something like that. Like if I just say 2, I mean this is a triplet. Use all that information. So here's the molecule. All right, so here's the molecule that gives rise to this spectrum. Now, I do want you to hit pause. First, hit pause, write in all the protons on this molecule, and then assign them. So, the protons on this carbon go to which peak? The protons on that carbon go to which peak, et cetera. All right? Come down and have some tea. So if you're not hitting pause, you're going to have to watch me drink tea. Okay, let's go on to the next one. Whoa, crap, no. Oh, yeah, so I'm going to do this. I'm going to do this on the board myself. So let's put in the protons. There's an H there, an H there, and an H there, right? End of a line is a CH3, so there's 3 protons. How many protons there? There's 2. 2, 3. All right, so there are our protons. Those are all the protons. Now remember, every peak in the proton NMR spectrum corresponds to a proton, and every proton has to match a peak down here. So let's just start off, like, here's a CH3. How many, so the question is, how many other protons are within 3 sigma bonds of these? Now you don't count themselves, okay? So 1, 2, these 2 protons are within 3 sigma bonds of each other, as are these 2 and these 2. But they're the same, they're magnetically equivalent, right? If I replace one of these H's, I get the same compound if I replace any of the 3. So these protons being magnetically equivalent means they give one signal, and they can't couple to themselves. Their signal will overlap. Okay, so one signal here. Now, let's go off. So 1 sigma bond, 2 sigma bonds, 3 gets me to a carbon. It doesn't get me up to the hydrogen, it gets me to that carbon. None of those atoms are magnetically active, right? 1 sigma bond, that carbon is 99.9% of the time going to be a C12, not active. O16s, C12. None of those are active, so this one should have 0 neighbors. What does a peak look like with 0 neighbors? Well, 0 plus 1 equals 1. It will be a singlet. All right, how many protons are there? There are 3. So the integration should be 3. So a singlet that integrates for 3, and now, what does it look like? Where in the chemical, what kind of chemical shift does it have? It's a proton on an sp3 carbon, right? This proton is tetrahedral. It's got 4 single bonds, so it's sp3 hybridized. That sp3 carbon is bonded to an sp2 carbon, right? This one is sp2. You'd expect, based on the chemical shift regime I gave you guys, that it would be somewhere between 2 and 3. So we're looking for a singlet with 3 hydrogens between 2 and 3. There you go. So what we might do is we'll say, let's assign letters to these. These are A, these are B, these are C. Make that different. C and D. All right, so A is going to correspond to that one. All right, no neighbors, so it's a singlet. 3 protons, so it integrates for 3. It's a proton on an sp3 carbon bonded to an sp2 carbon, so it's going to fall like 2 to 3. And remember, those regions are not like a wall. If it's 1.95, it could still be in there. It's kind of borderline. Okay, so if you didn't know what was going on before, hit pause and assign B, C, and D if you learned something by my assigning A. Okay, hopefully you're back. So let's look at B. How many protons are there? There's 2. So it should integrate for 2. All right. What about the chemical shift? Well, it's an sp3 proton bond, sorry, it's a proton bonded to an sp3 carbon bonded to an electronegative element, oxygen. You'd expect that to be, right, this is going to sort of be 3 to 5. Well, what do we have there? Oh, finally, how many neighbors does it have? Okay, so again, magnetically equivalent atoms can't be neighbors of themselves, right? I live with my wife. My wife is not my neighbor. She lives in the house. You probably have a roommate. Your roommate's not your neighbor. Your roommate, you know, is whatever relationship you have. So these 2 protons are going to make one signal. They're magnetically equivalent. Again, I have a video on that. I have some stuff on my PowerPoint shows that will show that if you need to look at it. These 2 protons are magnetically equivalent. So they're going to make one signal. So now, are there protons within 3 sigma bonds? And the answer is yes. So there's 1 sigma bond, 2 sigma bonds, 3 sigma bonds, and 3 there, right? So these 2 protons, proton C, are neighbors of B. So 2 neighbors. 2 neighbors plus 1 equals a triplet, 3 lines. Okay, so we need to find a signal that integrates for 2 that's a triplet somewhere between 3 and 5. And of course, obviously, probably you got there before me. So this one is going to be B. The 2 protons that I've labeled B are a triplet for 2 protons at about 4 parts per million chemical shift. All right, now you're down to 50-50. So how about C? Can you do proton C? Well, C, 2 protons. So the integration here is going to be 2. What about the chemical shift? sp3, you got an H bonded to an sp3CH, bonded to sp3C. It's going to be like 0 to 2 parts per million. And how many neighbors? So now the big question is, how many neighbors do proton C have? They obviously, if C is a neighbor of B, then B has to be a neighbor of C, right? I've got a neighbor named Jim, and I've got a neighbor named Kendall. Like, I am Kendall's neighbor, and I am Jim's neighbor. Jim and Kendall aren't neighbors. So proton C has at least 2 neighbors here with B. Does it have any others? Hit pause if you want. All right, yeah, it clearly does, right? So basically, when you're looking for neighbors, like if I'm looking for neighbors for this CH2, I just want to look at the atoms bonded to the atom that those protons are on. And so let's count the sigma bonds. 1, 2, 3. All right, so 1 sigma bond, 2 sigma bonds, 3 gets me to a proton. It actually gets me to 3 protons. So protons D are neighbors of C. Protons B are neighbors of C. So that's 5 neighbors. Plus 1 is going to be a sextet. All right, so I need to find a sextet between 0 and 2 parts per million that integrates for 2. And I've got one of those. So this sextet is protons C. Well, process of elimination. The triplet down here needs to be D. But don't just rely on that, right? Look at it. Actually, like, check it. Don't just say, you know, if you got 10 seconds left on an exam, write D here, move on. But in real life, you don't just say, well, we've eliminated everything else, so it must be that. Like, it could be your molecule's wrong. Like, think about what you're doing in the lab. In the lab, you don't really necessarily know it's this molecule. You're trying to check if it's this molecule, right? This is how, this spectrum is how we know we have this molecule. So check the signal down there. Check protons D. So again, integration is going to be for 3. Chemical environment is going to be the same here, right? Protons on an sp3 carbon bonded to an sp3 carbon. So 0 to 2 parts per million. And now how many neighbors does D have? All right. Remember, we decided that protons D are neighbors of C. Well, and that means C has to be neighbors of D. They're coupled. And like I said, my neighbor Jim is on my right. No, Jim is on my left. Kendall is on my right. They're both my neighbors, but Jim and Kendall are not next to each other, right? So D is a neighbor of C, B is a neighbor of C, but B and D are not neighbors of each other. They're too far away. 1, 2, 3, 4 sigma bonds. So the magnets, the little tiny magnets of B are a little too far away from D to really influence them. All right, so D has 2 neighbors. That'll give me a triplet. So protons D need to be a triplet that integrates for 3, somewhere between 0 and 2 parts per million. And that would be consistent with that signal. Okay? So that's how you assign protons to peaks. You can watch that again if you want. I'm going to go on to another molecule. I'm going to do it a little bit faster because I'm at 21 minutes, but I hope that made sense to you. You want to think about all of those. You got to make the neighbors fit, you got to make the chemical shift fit, and you got to make the integration fit for an assignment. Okay, so let's go back to the original molecule. This is the original molecule I put up a couple of videos ago. So again, hit pause, figure out where the protons are in this molecule, and then assign them to a peak in the proton NMR spectrum. Okay, so protons, you got 3 protons out on this methyl. End of a line is always going to be a methyl. No protons there, right? 1, 2, 3, 4 bonds on that carbon. Oxygen's got 2. We got 2 protons here, 2 protons here, proton there, proton there, proton there, proton there, and then 3 here. All right, remember, if you go back and look at the molecular symmetry stuff I did in the C13 NMR, there's a plane of symmetry down this benzene ring, so these 2 are going to be magnetically equivalent, and these 2 will be magnetically equivalent. So let's put letters by these. These are going to be A, B, C, D, and D, E, and E, and then these will be F. And again, when you have a benzene ring, right, a flat benzene ring that's substituted directly opposite each other, there's going to be a plane of symmetry running there. So that carbon is magnetically equivalent to that carbon, and that carbon, and the H's thereon are also magnetically equivalent. So these are both D, these are both E. All right, so using that, if you want to hit pause again and sort of, if you lettered them differently, sort of make heads or tails out of that, do so. Okay, so let's look at A. A, there are 3 protons, so the integration should be 3. Integration should be 3 because there's a methyl. How many, and then the protons here are on an sp3 carbon bonded to an sp2 carbon. That's going to be like 2 to 3 parts per million ish. And how many neighbors? We saw this on the last one, none. 1, 2, 3. 3 sigma bonds from the H gets me to 2 O's. So no neighbors there. And remember, magnetically equivalent atoms can't be neighbors of themselves. I don't have a clock. All right, so this should be a singlet, 0 to 2, sorry, that's not right. 2 to 3 parts per million, and it should integrate for 3H. Well, that actually fits 2 signals here. We've got 2 singlets. And you'll notice here, one's short, one's tall. They both integrate to 3. That means the short one's fat, the tall one's thin, right? The area under these 2 are the same. Both of these are singlets, integrate for 3 between 2 and 3. So either one could be A. Let's go over and look at F. You'll see why I want to here in a minute. 3 protons on F. They're all magnetically equivalent. So this should integrate for 3H. How many neighbors do they have? 1, 2, 3 sigma bonds. Don't count this. We're only looking at sigma bonds. 1, 2, 3 gets me to a carbon. 1, 2, 3 gets me to a carbon. Protons F have no near neighbors. So 0 neighbors is going to be a singlet. Protons F are bonded to an sp3 carbon, bonded to an sp2 carbon. So 2 to 3 parts per million. That's really similar to this one. And so here, again, this is one of those science things. The data at this point, and this spectrum, is not going to let you differentiate A and F. All right, both of these, one of those is A, one is F, but you don't have enough data to say which is which. Now again, this is introduction to organic chemistry. So there are more sophisticated NMR experiments we can do that would tell you which one's A and which one's F. Right now, you don't have that, and so it's fine. If this were like a homework assignment, you could just tell me these 2 protons are A and F. All right, let's go now to B. Again, B, 2 protons. Integration is going to be 2. H on an sp3 carbon bonded to an electronegative atom. That's going to put us 3 to 5 parts per million. Right, I know that from, and you guys are free to use the slides back a ways to come up with that. And now, how many neighbors do proton B have? Okay, again, the magnetically equivalent protons can't be neighbors. So 1, 2, 3. 3 sigma bonds gets me to proton C. If I go the other way, 1, 2, 3, I get to a carbon. 1, 2, 3, I get to an oxygen. So proton C are the only neighbors of B. So 2 neighbors is going to be a triplet. Okay, so a triplet between 3 and 5 that integrates for 2. I got 2 of those, just like over there. 2 signals that fit this. What about proton C? How does that look? So an integration of 2, and again, neighbors, 1, 2, 3 gets me to a carbon. 1, 2, 3. Well, we said C is a neighbor of B, so B has to be a neighbor of C. So again, 2 neighbors. That's going to be a triplet. Proton bonded to an sp3 carbon, bonded to an electronegative atom. 3 to 5 parts per million. It's the same as B. So B and C, just like A and F, we don't have enough data to differentiate. We don't have enough data to differentiate B and C. So these, all you can say are these 2 are B and C. We know that we know those 2 signals are B and C. They're not E, F, or A. All right, so now let's come. The only ones we haven't done are D and E. So again, we have 2 proton Ds. So D, 2 H's for D. How many neighbors do they have? All right, 1, 2, 3. So E is a neighbor of D. 1, 2, 3. Sorry, 1, 2, 3 gets me to an oxygen. 1, 2, 3 gets me to a carbon. 2 neighbors. It's going to be a triplet. No, sorry, 1 neighbor. Right? D has 1 neighbor, E. This D also has 1 neighbor. Both E's are not neighbors of D. So that's going to be a doublet. And there are, so 2, and then, oh, what chemical shift? This is a proton on an sp2 carbon. And it's a benzene. And so this is really going to be 6 to 8 parts per million somewhere. And we've got one of these. You see the pattern, I think, at this point. E is going to be the same thing. There's 2 E's. E has 1 neighbor, D. So that's going to be a doublet. And E is a proton bonded to a benzene. So this is going to be 6 to 8 parts per million, not 6 to 8 ppm. And so D and E are these 2. And again, there is not enough information for you to tell that that's D and that's E, or that's D and that's E. So again, don't go past the data. The data is going to take you so far. Go to where the data says and then stop. All right, so in real life, if I needed to figure out which one of these was, if I needed to know for sure that this signal is D and that one is E, there are more sophisticated experiments I could do. If you're a chemistry major, you'll learn them. It's a lot of fun. I find spectroscopy is a lot like a puzzle, putting it together. If you're not a chemistry major, you probably don't care. All right, so go as far as the data will take you and don't go any farther. All right, there you go.